Okay, here in section 4 we're going to look at limits at infinity. So we're going to be evaluating limits of functions as x is approaching infinity or negative infinity and see how those things are going to pan out for us. Alright, so let's think about the function f of x equals x plus 1 over 2x. Being a rational function, remember rational functions have these asymptotes, these kind of like boundary lines. And this function f would have a horizontal asymptote at y equals 1/2 and a vertical asymptote as x equals 0. Okay? So if we were to perhaps look at the limit of f of x as x is approaching infinity, okay? So you can see over here on this side, here's my x's are going to infinity over here. Okay, so x is going to infinity, and what is happening to the graph? Well, the graph is coming down and it's getting closer and closer and closer to this line of y equals 1/2. And even though it's going to get closer and closer and closer, it's never actually going to reach it. So the limit as we go to infinity is going to be positive 1/2. Okay. What about the limit of f of x as x approaches negative infinity? Okay, so now we're heading out this direction, and again the graph is coming up. As my x's are going to negative infinity, the graph itself is getting closer and closer to that value of 1/2. Okay? So as x is increasing without bound, the value of the function is getting closer and closer to being the value of 1/2. And the same thing as x is going to negative infinity. The function value is getting closer and closer and closer to 1/2, even though it never actually will reach it. So we can talk about the limit of f of x as x approaches infinity being some value L, we'll just call it L1, and then the limit of the function as x approaches negative infinity being some value of L2. Sometimes they're going to be the same, sometimes they may be a little bit different, just depends on the function, but generally those two values will be the same, but we'll be looking at them independently as infinity and negative infinity. We'll kind of look at them as separate cases. Alright, so if we have a function in the form of 1 divided by x to the r power, as x is approaching infinity, as x is getting larger here, as long as r is a positive value, that limit is going to go to 0. Because if I take 1 over a number, as that denominator gets larger and larger and larger, the value of the whole fraction approaches the value of 0. And the same thing happens when I'm going to negative infinity. Okay? As these denominators here increase in size, then the value of the fraction itself will keep getting closer and closer to being 0. Okay? And that exponent r has to be a positive real number. So we want that exponent being a positive real number there. Alright, so let's find the limit of the function. So if we use our rules, our properties of limits that we had, we could kind of break this up and say that this is the limit as x approaches infinity of 4 minus the limit as x approaches infinity of 3 divided by x squared. Okay? Well, the limit as x approaches infinity of 4 is just going to be 4. Okay? And the limit of 3 divided by x squared as x approaches infinity, that was the property we just saw. Okay, here's our x to the r down here in the denominator, so we know that that limit is going to be 0. So the limit of this entire function of 4 minus 3 divided by x squared, the limit as x approaches infinity, will have a value of 4. Okay. Limit as x approaches infinity of 3 plus x divided by 3 minus x. Okay, so we could look at this and say, okay, well, let's look at what would the graph of that look like. Let's think about the graph and see if we can get the limit from the graph. Okay, 3 minus x means I'm going to have a vertical asymptote. X cannot be 3. Okay, so we'll have a vertical asymptote out here at x equals 3. And horizontal, I've got the value, these two exponents are the same value, So the horizontal asymptote is going to occur at the coefficients of those x's, which would be a -1. Okay? So across here, boom, 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 boom. Y equals -1. Okay. So let's pick some values. If I were to put in 0 for x, then I get 3 over 3, which is 1. Okay. So if I put in 0 for x, I'm going to get 1 for y. Okay. So I got this point here. Let's say if I were to put in 1 for x, then I'd have 4 over 2, which is 2. So if I put in 1, I'm going to be up here at 2. Okay, so the graph is going to be doing something like this when these numbers here. And if I were to put in, let's say, 5, okay, 3 plus 5 would be 8, 3 minus 5 would be -2, so 5 is going to be at -4. So the other part of the graph is going to be down in here somewhere. Okay. But in either case, we can see as x is going to infinity, okay, we're looking down here, as my x's are going out to infinity, here's my function. It's going to be approaching this horizontal asymptote. So the limit is going to be -1. The bigger x gets, the closer I'm going to get to that value of y equals -1, even though I'll never actually reach it. Okay, here's another problem. Limit as x approaches infinity of -2x plus 3 divided by 3x squared plus 1. Okay, so we're going to do something a little bit different here. What we're going to do is we're going to divide all of the terms by the biggest power, which is the x squared. Okay, so I'm going to have -2 divided by x squared plus 3 divided by x squared, and all of that over 3x squared divided by x squared plus 1 divided by x squared. Okay. So when we simplify all of that stuff down, limit as x approaches infinity, -2x divided by x squared would be -2 over x, okay, plus 3 divided by x squared, divided by, that would be 3 plus 1 over x squared. Okay. So now if we think about some of the properties that we had for these limits, where we had that 1 over, okay, x to the r power, well, if I look at those, okay, the limit of -2 over x, as x keeps getting bigger and bigger and bigger, this is still going to 0. Same thing here. As x is getting larger and larger without bound, that's going to 0. Same thing here. That's going to 0. So what we ultimately end up with here is the limit as x goes to infinity of -2x plus 3 divided by 3x squared plus 1 is actually going to 0, because I would have 0 divided by 3, which is going to be 0. Okay? And we could check that, we could verify that with the graphing calculator by graphing the function and seeing that the graph would actually be approaching the x-axis as we head to positive infinity. Okay. So let's look at this one with the same approach. If I were to divide all of those terms by an x squared, by the largest power, I'd have -2 plus 3 divided by x squared over 3 plus 1 divided by x squared. Okay. Well, the limit of -2 as x goes to infinity would just be -2. The limit of the 3 divided by x squared, the limit of this piece right here, as x goes to infinity, is going to be 0. The limit of 3 is just 3. And the limit of 1 divided by x squared, that's also going to be 0, which means the value of my limit is negative 2/3. Okay? So by dividing everything by that largest power, we're able to kind of break these things down into things that we have properties of limits for. Okay? The constants here at -2 and +3, the limit of a constant is still going to be that constant. Okay? And these values of this 3, this 1 divided by x to the r, we've got these fractions here with our powers of x in the denominator, those limits always going to 0, so that we're able to break those things down into some manageable pieces and come up with our limits. Okay. So let's try this again. Limit as x approaches infinity. If I divide everything by the biggest power here this time is x cubed, so I'd have -2 plus 3 divided by x cubed divided by 3 over x plus 1 over x cubed. Okay. So what are we going to end up with here? Well, the limit of -2 is just going to be that -2. Okay. The limit of this 3 divided by x cubed, well, that's going to be our 0. Okay. But what is the limit of 3 divided by x? This is going to be 0. This one is going to be 0. So I end up with -2 divided by 0, okay, which is undefined. So what does that mean? Well, what that tells us is that the limit does not exist. Okay. So there's actually some patterns here that are in all these things, if you've noticed them or if you've figured them out yet. So sum those up and look what we're talking about here. Okay. When the degree of the numerator is less than the degree of the denominator, then the limit of the function will always be 0. Okay. If I've got a rational function and the numerator and the degree of the denominator, if those degrees are the same, then just like with the asymptotes, the limit is going to be the ratio of the leading coefficients, those largest powered terms. And when the degree of the numerator is greater than the degree of the denominator, like we saw in the last example, that means that the limit does not exist. Okay, it's not going to happen. So those are kind of 3 general rules, and they really follow the same guidelines as we had for finding those horizontal asymptotes, because those horizontal asymptotes of those rational functions ultimately are the limits. Those are the boundaries that the graphs are approaching. Even though they never reach there, they're going to keep getting closer and closer and closer, and that's kind of our idea of a limit as well, is that we're getting super close to something, but sometimes we don't always reach it. It's like our boundary. It's like a ceiling. Okay. So, last but not least, make sure you bring your books to class, because we will start working on some problems having to do with these limits at infinity. Okay. We'll see you tomorrow.